if we want to compare the precision of two sets of data, and quite often in chemistry what we do, we might be developing a method that we think is more precise than the existing method. So in that case it's actually a one-tailed test, because you're asking the question, is the precision better or not? Has it been improved? You're not asking if it's different. So if it's just different, either better or worse, then it would be two-tailed. If you're just looking for if it's better, then it's one-tailed. Either way, we would do an F-test. An F-test is just a simple test where you're actually comparing the variances of two methods. So remember, variance is standard deviation squared, and we usually pick this so that the number on the top is bigger than the number on the bottom. So if we have two sets of data, let's say we have method A and method B, we're just trying to see if maybe B is the old method, A is the new one. Is it better in terms of precision? And the new method gives us 11.2, 12.3, 11.5, and 11.8. And then the old method is 12.8, 11.1, 10.5, and 13.2. So it looks, just by looking at numbers, like the old method might have poorer precision. So what we do is take the variance for both. So the variance, which is just a standard deviation squared, if you do it for method A, the first method, that gives you a variance of 0.22, and B is 1.7. So to get F, we just divide the bigger number by the smaller number. So it's 1.7 divided by 0.22, and it gives us an answer of 7.73. Now we'd have to look up, so this is the experimental value, to look up the critical value. So you go to a F table. There's usually, there will be two types of tables, one for a one-tailed test, one for two-tailed. So we want to look up for a one-tailed test, and remember we're looking up for degrees of freedom. So these tables are in terms of degrees of freedom of the numerator across the top and degrees of freedom of the denominator going down. So we have two sets of data, 4 observations each, so 3 degrees of freedom each. So 3 in the numerator, 3 in the denominator gives us a critical value of 9.277. And because the experimental value is lower than the critical value, we accept the null hypothesis, which says that there's no difference between the precisions of the two methods